Hello, dear students. So today's lecture is because in our previous lecture we have discussed about the vector transformation and also the completeness relation we have discussed about, right? So completeness relation is basically when you take that these 1, 2, and 3 corresponds to, if we have this one, this is our first element, that is 1, 0, 0, and 1, 0, right? And with the help of this, if you take the outer product, because this is the outer product, and similarly in previous lecture we have also discussed what is inner product, and inner product is simply the scalar product also, and that purely gives you the scalar number, right? But this is again a vector because you are taking the this first cat take its product with the bra of another vector, right? So that's it's also a vector, right? But the earlier one was that if you take bra with cat, bra, first bra then a cat, product of bra with cat, so that purely gives you a scalar number, you can say, right? And this is the property, this property is known as completeness relation. And so with the help of this relation, we can also prove that if you take, because our if a vector, if you write in some Euclidean in some three-dimensional space, so you can write that a can be written as that ax I cap plus a by j cap plus az k cap, right? And if you, with the help of this completeness relation, we can prove that if you take the product of this I with a, so this gives you ai, right? So we have, so you just check that my previous video, so we can prove that I with a equal to ai, or you can write this I dot a will be a of x. So what does it mean? So it says that अगर हमारे पास if our this vector a is known, अगर हमें a vector a पता होगा, so we have some vector in some three-dimensional space, right? So we have some three-dimensional space here, this x y z, and this our vector a, right? And it has those all the three components. That means ax, ay, and az, right? Now, if you want to calculate, so that means, so this relation tells us that if our total vector is known to us, so we can calculate then the different components of that vector by taking it as this inner product with different basis vectors with I, j, and k, right? Because when you take a with I, so that gives you the x component, ax component, right? And similarly, if you take the j with the j dot a, so that gives us aj, ay, and similarly for z component, right? So this is the property that, so first it should fulfill this property that these basis vectors, they are closer, or they should obey this completeness relation, right? And with the help of this relation, I can also prove the reverse of that. So that means if instead of that, because we can write this, if we have this identity matrix, we can write that 1 will be equal to, it will be equal to that summation over alpha with alpha. So this is very clear because if you take that alpha equal to 1, 2, 3, so this is again that completeness relation. So this is again completeness relation, right? Okay, and because this is equal to 1, it can be some identity matrix, okay? Unit matrix, right? And so if you multiply it by, so if you write now, okay, so you multiply it by some, we calculate this, okay, we can calculate now some a vector, so that will be equal. Okay, so no need to write because it's clear to us, so you can write it this way also. Now, so what is this one? So if you write this alpha with a, so this is following this relation. So following this property, yeah, this I with a, that gives us this, that component of that. If you take the inner product of some basis vectors I with some vector a, so it gives that the projection of that. It will give that component. Means I with a gives you the a component. If you take j with a, it gives you the aj component. So similarly, if you take the inner product of this alpha, right? Alpha can be any number, or these are can be I, j, k, right? With a vector, so it gives you the alpha component of that a. right? So we can write now, because our this will be equal to yeah, right? So if I check, if I use this property, because we have this I with alpha, so that is equal to, so okay, right. Or you can rewrite this as, so just check. So this is our another relation, or you compare this equation. Suppose this equation A, or you can, so some equation first we can write here, because I already use A here, so in order to avoid confusion, so you write this equation first and second. So अगर हम इनको compare करेंगे, if you check these, compare equation first and equation second, so what does they indicate, right? So first indicates that if you know the component of, if you know the total vector A, if you know the total vector A, and take it as dot product with some basis vectors. So basis vectors here alpha, it can be some I, J, K. So it gives you the corresponding component. Like if it will be I with, if it will be I with A, so it gives you the AI component or AX component. And if you take J with that A vector, so it gives you the AJ component, right? And similarly, so comparing this equation first with equation second, so this is, you can say that this is the reverse or reciprocal of equation first, right? So it tells the reverse of that. तो यहाँ पे मुझे कह रहा है, ये इक्वेशन मुझे कह रहा है कि अगर मेरे पास, if you know the some component of a vector, अगर मुझे कोई component, if I have some vector A, if I know that, so we have some vector A, right? Okay. तो अगर मुझे, if I know this, the first component of that vector, अगर मुझे ये पता होगा, if I know the component of that vector, right? Only one component of that vector, and you need to take it as this product with the cat state of some basis vectors alpha. So that gives you the total vector A, right? Only knowing the one component of that, right? So that means this equation second is the inverse of equation first, right? Either you know the component of a vector, you can calculate total vector, or if you know the this total vector, you can calculate the individual components, right? So this is clear from this equation first and equation second, right? Now coming back to this equation, so we can check one more property. So that is, if you talk about now, if we have, because as I already told you, if you take the outer product between these basis vectors, it gives you simply a vector. It can be some square matrix, right? So you can write now, because if we have, suppose I write here, if I have this, if I write some a square matrix, if I write some square matrix. Suppose I have some square matrix, some M, or you write some, okay, so that's clear. So that's equal to some, because this is the outer product between the matrix, these vectors, right? So this is purely that square matrix, right? Because if you take this, because so suppose you have this, suppose our A is, let me write, so let me write its component, because this can be column matrices, so you can write this as, this will be some ABC, and if you write that C, cat of C, so it can be some D, right? So you just check my previous lecture. So you can, if you take the outer product A with C, so right, so we have two vectors A with C. So take their outer product. So this will be simply that square matrix, 3 by 3 cross 3 matrix, because We have three components here because I'm saying that our vector is some Euclidean space. So you can have this total vector when you take the outer product between this A and C. So it will be purely a square matrix, right? Now my question is that we can find the different components, different elements of that square matrix, right? With the help of this completeness relation. So I'm basically discussing this time. So the application or the importance of this closure, this completeness relation. So with the help of this completeness relation, we can prove that we can calculate the different components of some square matrix, right? So as I already told you, I'm saying that my square matrix is some A with C, right? So we can write then. So we need to find. So we need to find some alpha beta, some alpha beta elements of this, right? Or suppose I want to calculate. Suppose my alpha beta is M12. Okay. So I need to calculate because our square matrix can be, because if you write it, because our square matrix is this M alpha B, alpha beta will be equal, so it can be this one. Okay. So because you can have the different, because M11, so this will be our square matrix, right? Because if you take that A with C, so just check it. So when you take this A with C, so this will be that AD. So it will be ADBECF. Then similarly, you can, because you will get that BDBEBF, and similarly CDC and CF. So that means जो हमारा matrix यहाँ पे होगा, this A with B, so it will be square matrix of this type, right? Because when you take that element, so it's clear because you just checked my previous lecture, so it is because it will take them time. So you can see that when you take their outer product between A and C, so it can be our it will be our square matrix, right? Of 3 cross 3 matrix, you can say, right? Okay. So let us calculate now, because my interest is to calculate. We need to calculate M12 component. So that means I need to calculate this component M12, right? So we can calculate this with the help of this relation. So if I write now, because our matrix can be, so we need to calculate this one with, I need to calculate this one, right? So because our matrix is known to us, you can write this as, okay. So this will be equal to, okay. So this is simply that when you take that bra of one, because one corresponds to our first component, so it can be some 100 component, right? So this is what I wrote here 10, because when you take bra, it is a complex conjugate of dual to that ket state, right? Okay. Because you are taking the complex conjugate of that this ket, that gives you the bra state. Okay. So when you take the multiplication, so this gives us one, right? So just check, because when you take this 1 with M11 will be 1, plus this M12 with 0 will be 0, this will be 0. So it will be 1 0 0. So M11 plus 0 0. So it will be M11. Similarly, when you take 1 with this one, so then 0 with this, 0 with this. So that means the product between, when you take the inner product between that, sorry, product between this one with this M square matrix, so this will be M11, M12, M13, right? Now, because my interest is to calculate this one, I want to. So this you can rewrite this as this will be 1. So this will be equal to. Okay. This will be equal to, right? So that means with the help of this completeness relation, you can say that. So we can calculate the different components of a square matrix. So that means knowing the square matrix, we can calculate it as different components with the help of this property. So this is very clear because when you take one and two, so this gives you a1 2 because take the product, so only this one second component will survive because this 0 with this will be 0, a1 2 with 1. So only the second component will survive here, right? So this is the way how you can calculate the different components of a square matrix, right? So that means I can write in general, if I want to calculate that alpha with beta, right? So that will be equal to, right? So that means अगर मेरे पास so if it will be 1 1, and similarly if I want to calculate this 2m3, so this gives me m2. So following the same procedure, you can calculate the different these elements of that square matrix, right? With the help of this completeness relation, right? So this is very clear, right? Now, in addition to that, we will also learn how to transform. So how to transform in different bases. So how to transform in different bases use the Dirac notation also, right? So we can also write here. We will learn how to transform in different bases. Right, because this is that bracket note, which is also called a Dirac notation. So this is what I wrote here. Because how to transform in different bases. If I go from one base to another one, right? So how to transform in different bases using this Dirac notation, right? Now, so we can write. So let me rewrite that. We have this relation that you can write this one will be equal to that. It will be summation over I. Okay. Or if you multiply it by some vector A, so this will be equal. Okay. I am simply multiplying here the cat state of A, right? And if you check that, so this is our A because you are simply multiplying it by 1. So this A, so this will be summation over AI, right? And this will be equal to AI. Okay. Or okay, so that's clear. So if I multiply it by some parameter alpha here, so that means our vector A is equal to. So you write that. So just check whether if I'm right, summation or I right. So let's multiply here by some alpha. So this is equal to. about AI? It is simply that component. So I, if it is X, it can be some AX, AY, or AZ component. Right? So this is simply component. So you can write this as, okay, or you can write this as. So what is this one? So following that property, so you just check that property. If I write here, so which property I have to use? Okay, so this one. So because so I with A is AI, right? So using the same property, then alpha with A will be alpha. So that is equal to summation over I. Suppose this will be some prime, some new frame of reference, right? So I'm going in some different ways, right? Because I'm multiplying here alpha, so it can be some new basis, right? So I is some, we have some these orthogonal bases ijk, right? And these are some new bases that I multiplied with this. So that's why I put here some prime. So a prime alpha, so that will be summation over I, and this will be equal to alpha with I, right? So that means what is the form of this? So this is purely our scalar, right? So this is the inner product between the two different bases. So first is that IJK, these orthonormal bases, and these are some new bases, right? So this can be some kind of a transformation matrix, because I'm saying now I'm basically I'm basically changing this vector A from some AI basis to some A prime alpha basis, or from A prime alpha basis to AI basis, right? Is it okay? Because these are our new bases. So that means I am basically transforming this vector A from some basis to some new basis using the Dirac notation, because this is Brocken notation. So using this Dirac notation, I am basically changing the basis from one to another, right? So alpha is our new basis, this is our old basis, right? So that means this will be transformed to some, this A prime alpha will be transformed to A. So that means the product, inner product between the bases alpha with I. So it will be some transformation matrix. It can be some differential element, I can say that, right? So instead of that, I can write here. So this will be equal to. So you can write this as. So you can write this as. So this will be summation over I. And you can write this as partial xi x prime alpha. So just check. So that means this transformation matrix. So what I wrote here. So a transformation matrix is that's partial x prime alpha, this partial xi. So it can be some delta prime alpha I. It's a conical delta, right? So that means in alpha prime equal to I. So this delta prime alpha by I equal to 1. So when you put alpha prime equal to I, so A prime alpha will be, because I will be alpha prime, so A alpha prime will be equal to A alpha. So that means this will be our that conical delta, and this is our transformation matrix. So it basically helps us to transform from some old basis to some new basis, right? So that's how you can write this A alpha prime in terms of AI, right? So these are some properties that I have discussed today. These are some properties of this completeness relation, and how to calculate the different elements of a square matrix, or if you want to change the basis from one basis to some new basis using that Dirac notation, and how it helps us, and how you are getting this transformation matrix. So this, with the help of this transformation matrix, you are able to go from one basis to the new basis. Right? It's like we are going from some rectangular coordinates, some x, y, z, to some this cylindrical coordinates rho, phi, and z, or from rectangular coordinates x, y, z unit base where these unit base are x cap, y cap, z cap to some the spherical polar coordinates, that's r theta, r cap, theta cap, and phi cap, right? So with the help of this transformation matrix, we can go from one coordinate system to another coordinate system also, right? So these are some properties that I have discussed today. So in our coming lecture, we are going to discuss about those matrix tensors, and these are very so this is our this also called fundamental tensor also. Hopefully, we'll discuss that in our coming lecture. Thank you very much.